Меня зовут Никита. Вот, сейчас я магистр второго курса. Вот, занимаюсь, в частности, в своем дипломе, дипломной работе, интернализацией, разных физических аспектов, в, гомотопической теории типов. Вот, и, собственно, меня давно интересовала проблема гравитации. Вот, значит, было всегда удивлением, что неужели не хватает математики, чтобы как-то продвинуть наше понимание, лучшей природы гравитации. Вот, потому что уже прошло 100 лет, много было прорывов сделано, в теории струн, например, и так далее. Вот, но теория струн так и не построилась пока, вот, несмотря на 2 революции. Ам, Какое-то отношение она имеет к природе точно, но мы не знаем какое, вот. Но при этом, всё равно как бы совместить, гравитацию с квантовой теорией как-то не удалось. Вот, проблема эта концептуальная, как мы вот обсудим сегодня. Вот, концептуально важная, потому что если не решить ее, то у нас будут противоречия, значит, физики. Ну вот, ладно, тогда начнем. Сейчас переключусь на английский. Well, in the first lecture, I would like to make a brief introduction into what we are going to discuss in this course. First of all, let me outline a plan of this lecture. Well, of course, in order to be able to analyze the nature of gravity, we have to take into account the historical background on how our understanding of gravity has changed. Further, I shall notice the following pattern that each time when gravity was refined towards something much more deeper, a paradigm shift in fundamental physics happened. And we shall demonstrate it on the Einstein's theory of general relativity. So the main motivation for us is to understand the basics of inconsistencies of gravity with quantum theory, why they occur, and how do we plan to resolve some of them. And of course, this course of lectures is supposed to shed a light on the true essence of gravity, and we shall try to exploit the tools of homotopy type theory, cohesive homotopy type theory, in order to resolve some issues concerning gravity. For example, the so-called topological incorrectness of gravity. Let's move on further. And of course, this whole framework is about the Hilbert's six problem, which states the problem of finding a mathematical foundation for the existing fundamental physics. And I would like to notice that this is an introductory presentation, so we shall not focus on details and examples today. But of course, further in the course of lectures, we shall use lots of examples as physical and mathematical in order to motivate and move ourselves further towards a better understanding of gravity. Well, the history of gravity began from Newton in 17th century. Everyone knows Newton's equations. well, there are second-order linear differential equations in Euclidean space. We shall discuss Newton's gravity a bit further. Later, 100 years ago, Einstein came up with his general relativity, and gravity has become an incarnation of both principles of equivalence and a Lorentz covariance. And the mathematical foundation unexpectedly has become a pseudo-Riemannian geometry on four-dimensional smooth manifolds. It was a tremendous contribution at that time, and as far as I'm concerned, to see the geometry of curved spaces in physics at that time was very unexpected. And so gravitational field now has become a metric tensor, to be more precise, a pseudometric tensor, satisfying locally the famous Einstein's equations, which locally in coordinates look as follows. Well, on the left-hand side, we have the so-called Einstein's tensor. It is compounded. It contains all the curvature data concerning the geometry. And on the right-hand side, we have the so-called energy momentum tensor. Energy momentum tensor is a function of fields, some sections of bundles over the manifold, and the metric tensor. So the right-hand side describes matter, as physicists say. Yes, there are lots of different modifications of Einstein's gravity. Despite the fact that Einstein's theory is very successful, it has some minor and major drawbacks. And conceptually, the Cartan's understanding of gravity is much more modern, I would say. So a minor modification of gravity, such as Einstein, Cartan, Hilbert, and Palatini modifications, are concerned with the Cartan geometry, defined by the inclusion of these Lie groups. And gravitational field now is a couple. First of all, it is a spin connection. It is some SO13 valued connection on the manifold. And the other part of the gravitational field is the so-called Wheel-Beam or tetrad field. Mathematically, it exhibits a reduction of a frame bundle to the Lorentz group. And these variables must satisfy the early Lagrange equations of the following first-order Lagrangian form, where F stands for the curvature of the spin connection, E stands for tetrad field, and epsilon is a totally antisymmetric tensor. Well, of course, there are many other modifications. Some of them resolve cosmological problems and etc. But we shall not dwell on these modifications, since conceptually nothing yet has changed from the first half of the 20th century. So gravity nowadays is almost the same as at that time. The following pattern is quite eludes me. So each drastic step towards a deeper understanding of nature of gravity accompanies a paradigm shift in fundamental physics. Well, I'm sorry for resolution, but we have what we have. So Newton's gravity accompanied second Newton's law, Basically, Newton's gravity was empirical, because it came out of celestial observations, and so on. Well, the source of gravity is a mass distribution. Well, trajectories of moving particles now are parameterized by an absolute time. Absolute means that this is only the parameter and satisfy Newton's equation. Let's move on to the Einstein's general relativity. It has appeared as a pure logical combination of Newton's equivalence principle with Lorentz invariance. Well, Newton's equivalence principle states basically that it is impossible to define to observe the difference between a free-falling free moving body in an accelerating reference frame with a body moving in a gravitational field. So in principle, these are the same. So moving in a gravitational field is basically moving freely, but in some accelerating reference frame. Yes. And Lorentz invariance firstly was observed in electrodynamics. Maxwell equations they possess Lorentz invariance, which suggested that field theory needs to be in field theory, space plus time construction needs to be replaced by space-time, where time and space are now only the parameters of some four-dimensional manifold with a Lorentz Poincare group of symmetries. So let's move on further. Source of gravity now isn't the only mass distribution. It is a common mistake to assume that mass is a charge of gravity. No, of course, the energy density is a charge of gravity. It means that, for example, if you consider a vacuum electrodynamics, it has no mass because photons, for example, have no mass. But nonetheless, even the vacuum electrodynamics has a non-trivial energy momentum tensor, which yields non-trivial solutions to the Einstein's equations. Yes, the source of gravity now is the energy density of a field content, which interacts somehow with geometry. Well, interacts means that geometric data somehow is a part of a definition of our field theory. Well, effect now is that we have a curvature of space-time. Its implications, such as time dilation, gravitational lensing, formation of black holes, and etc. Now these phenomena are new to us. So we see that Einstein at that time has made a great and tremendous contribution to a deeper understanding of gravity. Well, let's move on further. We have the following paradigm shift. We have a principle of superposition. We know that most of the field theories are quantum in nature. But on the left-hand side, we only have some hints or question marks. We don't possess any gravitational theory which would accompany the paradigm shift towards the quantum theory. And so far, it is an open problem. Well, despite the recent advances in stringy frameworks, or some attempts to axiomatize quantum field theory, the true nature of the theory of gravity is yet far from being clear. And in our course, we'll try to make a little step towards a better understanding the nature of gravity. But we shall exploit the tools of homotopy type theory. Why gravity is incompatible with quantum theory? So far, Einstein's theory is accepted by scientific community and is famous for its great success. But what's the problem with it? Of course, concerning the compatibility of gravity with quantum theory, there are problems of both the technical nature and the conceptual nature. So the first one is of the technical nature. It means that despite the fact that we cannot resolve this problem only reflects that we have to change a mathematical foundation for gravity, but it doesn't imply anything of the conceptual at the conceptual level. The problem of a time choice. It occurs when quantizing gravity as a field theory directly. A time in gravity becomes a gauge parameter. Which leads, in addition to the fact that Hamiltonian of gravity is a sum of constraints, it implies that either the diffeomorphism invariance of gravity is broken at the quantum level, which is quite bad, I guess, and on the other hand, there is no dynamics. Thus, no observable implications of quantum theory of gravity. So if someone is struggling to understand what's going on, it's not bad, because we shall delve deeper into that in the next lectures. Well, this problem of a time choice usually can be resolved in analogous cases by finding another time, which is defined purely by variables of the theory. For example, when you quantize a three-point relativistic particle, you shall encounter the same problem, that you have no dynamics in quantum theory. But it can be resolved. But nonetheless, in the case of gravity, so far, it isn't the case. There's no solution to time problem of gravity. If you have one, you shall be very successful. Another issue is quite conceptual. Well, I've tried to make it quite redundant, but nonetheless correct. Well, this problem states that it is impossible to measure things at small scales. If we combine gravity with quantum theory. To be more precise, given the uncertainty principle of quantum theory, we have that in principle we can measure momenta and coordinates up to some up to some h Planck constant. On the other hand, when we have gravity at our hand, it implies that black holes may be formed when we put so much energy into the region of space. And black holes are formed with radius less or equal than this value, where m is the mass which you put in a small region of space. Well, if we fill the space with particles of energy or momentum, um, then we may assume that mass is proportionate to the momentum. It will yield a black hole of radius estimated by this parameter. Introducing the square root of GH and calling it L Planck, where we conclude that but by trying making an observation at a small region, black holes are formed. So it makes it impossible for information to get out from this small region. And estimately around this scale, all measurements are impossible according to the existing theories of quantum theory and gravity. So this is a conceptual inconsistency. Well, there are many other conceptual inconsistencies, like causality violation, of course, but let's move on further. So let's discuss our plan, what we are trying to resolve and understand in our course. First of all, we shall exploit recent advances in cohesive homotopy type theory by Urs Schreiber, Hisham Satie, and others, and try to understand how fundamental physics internalizes naturally and simply in the context of higher topos theory. For example, classical and pre-quantum field theory both are described within the so-called higher pre-quantum geometry. Well, in further lectures, we shall try to discuss that in great detail. Quantization, now abstractly understood well as a motivic linearization of pre-quantized phase infinity stacks of field theories. Well, concerning the quantization procedure, we shall touch it a bit in our course, but we don't need the motivic quantization in great detail. So we shall not concentrate on it. Cartan geometry as a cornerstone of existing gravitational field theories. And these internalize naturally in differentially cohesive infinity toposes. So general relativity, type 2, supergravity, heterotic supergravity, etc. All appear naturally within the context of differentially cohesive infinity toposes. Quantization, non-perturbative, of course, is a topological procedure. This is one of the main points that we're trying to make. That when we quantize theories, we exploit the topology of the phase spaces, and in particular the topology of manifolds within we consider the field theory, the particular field theory. Well, quantization is a topological procedure which exploits information on underlying homotopy types of the phase infinity stacks or phase spaces. And we shall see that even introducing some symmetries in our theory leads to deformation of the homotopy type of its phase space, which consequently reflects for example, some physicists are aware of 3D Chern-Simons gauge field theories on on a manifold sigma. Field configurations are gauge equivalent if they are joined by a diffeomorphism of a manifold sigma. It is quite a known fact. And thus, the theory is implicitly generally covariant. Yes. But nonetheless, if we'll try to make the theory explicitly generally covariant, general covariance means that the theory is invariant under diffeomorphisms of our base manifold. Well, explicit general covariance means that the configurational stack has now become a quotient 2 stack. And these theories may be different at the quantum level, which is quite peculiar. And some information concerning this one may find in the book this book by Urs Schreiber. So even an inclusion of symmetries into classical theory may yield changes in quantized theory. Since the homotopy type of configuration infinity stack is deformed, we now have the structure of a quotient stack. And this deforms the homotopy type, and as a consequence, deforms the quantum theory. Yes. Another point, which is very important for us, is that field theories classically are defined by local systems of Lagrangians. These theories need to be pre-quantized before the quantization, and this procedure is incoherent with gravity. The main point is that, of course, we shall discuss that further in great detail. We shall prove lots of theorems, but now only words are possible. We shall discuss further that regarding a pre-quantized field theories which interact with gravity and have a non-trivial underlying topological class, one may encounter an abstraction to glue the geometry globally by only solving the Einstein's equations on an open cover of a smooth manifold. So basically, it means that gravity is incorrect when we try to consider it globally or topologically on a smooth manifold. What if we want to go further and allow our smooth manifolds to become orbifolds, or rather more general stacks? How do we define gravity there? So these questions don't have final answers. And the Einstein's theory exploits the structure of a smooth manifold, but we expect it to be able to describe gravity on orbifolds or on smooth manifolds with singularities. Why not? So our goal is to refine gravitational theories, such as Einstein's theory, to such form so as to make them compatible with pre-quantization of interacting with gravity fields. Refinement process shall reveal that gravity cannot be put together with normal field theories, but instead it should be what we shall call a parametrized field theory. This means precisely that gravity is not described by the usual Lagrangian, but instead it should be described by some endofunctor on the category of parametrized homotopy types over the topos of algebras over the jet command theory. So gravity still remains about the Cartan's geometry, but now a source of gravity, in addition to energy density, is a topology associated with the field content. Well, the question mark is added in order to induce some mystery. So we shall extensively use the tools of higher topos theory to construct a refinement. So we see that we have a problem, and this problem can be resolved extensively using the higher topos theory. From the first sight, it might seem that seeing higher topos theory in physics or in gravity context seem to be quite unexpected and unnatural. But we remember that 100 years ago, seeing the geometry of curved spaces in the context of physics was very unexpected. So we return to the above table and we see that quantum paradigm leads to a shift from the pseudo-Riemannian geometry with gravity as a classical field theory to higher topos theory, with gravity now understood as a parametrized field theory. So yes, let's move on to the mathematical aspects of our discussion. Of course, I presume that listeners are familiar with toposes, higher toposes, and so on. So here I only remind some of the main aspects of the theory. Well, a topos is basically an abstract category where one can reproduce the known mathematics, set theoretical mathematics. A topos is a left exact localization of a category of presheaves of sets. These localizations are classified by Grothendieck topologies. So any topos has a form of sheaves on some side. An abstract characterization of toposes is presented by the very well-known Giraud axioms. The category H is presentable. Well, it has small colimits and a set of small generators. Colimits are universal. It means that colimits are preserved by pullbacks. Coproducts are disjoint. Well, equivalence relations are effective. Well,
меня слышно?
Yes. Да.
Кажется, что не все люди понимают эту локализацию, перспективную локализацию, это только у Ури такое соглашение было, то есть, возможно, стоит сказать, что локализацию просто часто называют там, в произвольном классе стрелок, а мы тут имеем в виду рефлексивную категорию.
Left exact localization. Ну, нет, в целом-то это и есть локализация по классу стрелок.
Да, но это частный случай.
Да, имеется в виду, что, давайте на русском, что это рефлективная подкатегория. То есть левая рефлективная подкатегория и рефлектор точный слева. То есть он сохраняет конечные пределы.
Например, там специальное множество, если локализация слабых эквивалентностей, это будет нерефлективная локализация. То есть вот такое мы тут не рассматриваем. Да,
в симплициальных множеств вообще левых таких локализаций нетривиальных нет. Вот. Да. Well, a topos theory is a home for the so-called abelian sheaf cohomology. What is higher topos theory? Well, we have infinity categorical analogs of the Giraud axioms. They sound basically the same, But now equivalence relations are understood as groupoid objects, and they're supposed to be effective. It means that effective epimorphisms, the category of effective epimorphisms is equivalent to the category of groupoid objects. Well, if someone is struggling to understand that at this moment, uh, we shall consider that in great details in further lectures. So, well, higher toposphere is a home for any type of cohomology. And the Brown theorem holds within toposes because, yes, it holds, well, it exhibits the cohomology theory as a study of home infinity groupoids in infinity toposes. Yes. Well, I've made that terrible copy from a book by Urs Schreiber. It is a short table which represents how zero axioms are represented in terms of the principal bundle theory. Quotients are effective means that every quotient may be considered to be principal, or equivalently, every effective epimorphism is a represents some groupoid object. Well, another axiom is that colimits are preserved by pullbacks. It means that non-abelian sheaf cohomology or simply non-abelian cohomology classifies infinity bundles. So this is the main, or one of the main aspects of higher topos theory, is that cohomology always classifies something. So, for example, as we shall see, differential cohomology classifies, for example, gauge field configurations, and so on and so forth. So our framework works around the Hilbert's sixth problem. Historically, it sounded, as far as I'm concerned, like this. The investigations on the foundation of geometry suggest the problem. We need to treat in the same manner by means of axioms those physical sciences in which already today mathematics play an important part. And so far, we have the following table, which I copied from the book by Urs Schreiber. It sketchily represents the correspondence between physical constructions and some mathematics. So, for example, mechanics of 19th century now has a form of symplectic geometry. Gravity is a pseudo-Riemannian geometry. Gauge field theory is understood as a Chern-Weil theory. High gauge theory is represented by differential cohomology. Quantum mechanics, for example, is represented by operator algebra, and so on and so forth. And recent advances concerning the local field theory have been made by infinity n category theory. Well, the foundations of fundamental physics internalize in higher toposes, as these capture the basic principles of current physics. One of the principles is the gauge principle. It states that field configurations, which can be joined by gauge transformation, may be physically equivalent. It means that when we are working with gauge theories, or theories where a gauge principle, the gauge principle is present, we are working with homotopy types. Principle of locality. Well, it's quite crudely stated, but so far it reflects the idea. A principle of locality states that we postulate a notion of geometry and how these geometries and structures of a dam can glue, local to global data. Locality means that the physics is built out of structures that glue the local information to global and vice versa. So meaning that any such structure defined globally can be represented as a local plus gluing. Principle of superposition states that spaces of states of matter field theories must be linearized in some way, states decompose as sums of different states. This is the so-called principle of superposition in a very crude form. Another motivating point for us is that infinity topuses themselves serve as some sort of a substances for constructing mathematics and thus for building their fundamental physics. We have, I've used the following table taken from NCAT Lab. This table represents the correspondence between very well-known physical constructions, their differential geometric incarnations, and their reformulation inside the higher topos theory. Gauge fields now represented as cocycles in some differential cohomology. You can see this table. Let's proceed. Concerning the quantization, quantization now is well understood as geometric and algebraic quantization, and both these aspects are parts of the so-called motivic quantization. Here we can see that the process of quantization briefly. We have an action functional, which now is represented by cocycle in U1 differential cohomology. And then we have some E infinity ring E. Via the representation of U1 group, we obtain a linearization of the space of configurations. It's all very crude, but we need to draw some understanding of what is going on in quantization, in motivic quantization. How the internalization into the higher toposphere works? Differential geometry or topology is almost about studying differential cohomology. Cohomology is about studying home infinity groupoids in infinity toposes. And differential cohomology is concerned with studying home infinity groupoids in cohesive infinity toposes. Infinitesimality in differential geometry. There are lots of constructions such as jet bundles, tangent vectors, Lie differentiation, etc. They all can be internalized within differentially cohesive infinity toposes. Yes, if you have any questions, you may ask. Why is it impossible that physicists has avoided the homotopy type theory so far? Urs Schreiber has an opinion on that, and I shall use that because I fully agree with that. From this perspective, the true global effects of physics appear as if a departure from normal and are accordingly called anomalies. While this is while the perturbative perspective is very useful for many computations and often good approximations to a complicated reality, fundamental formulations of fundamental physics must instead take all these global effects, like anomalies, into account. And for practical matters, this is the central role for the application of high differential geometry and differential cohomology to physics. Differential cohomology is a theory of global effects and of anomaly constellations in field theories. And while the gauge principle is widely hailed as a central principle of modern physics, many discussions of mathematical physics ignore it. Well, there's some troubles with my presentation. I'm sorry about that. In short, people have managed to avoid homotopy type theory because they worked locally and avoided such problems like anomalies. So physicists who have worked with anomalies are very well aware of such theorems like Atiyah-Zinger index theorem and etc., because these exploit the global topological structure of a smooth manifold where the field theory is considered. So this lecture is supposed to be quite short because, we cannot afford ourselves to delve into the subject matter deeply. We need many prerequisites, but we have the plan to the next lecture. What is classical field theory? We shall outline that strictly inside of the toposes, cohesive toposes. What is quantum theory? What are the fundamental forces in the standard model? The standard model is one of the cornerstones of quantum theory, and we shall discuss some of the aspects of it. And what is gravity overall? We shall state the problem that we are trying to resolve in our course strictly, and we'll try to resolve that. Thank you for your interest. This lecture was supposed to be quite short, so if you have any questions, I'm fully yours to answer them.
Спасибо. У меня не получается включить камеру, к сожалению. Вот, но...
Да, кстати, сейчас я выключу запись.
Okay.
Слушай, я и не записывал, так что хорошо, что ты записывал.
Я так и подумал. Я еще подумал просто спросить, случилась ли запись, но...
Когда-нибудь поиграть с так называемой D-геометрией. То есть это, например, по сути, перенос дифференциальной геометрии, там, струйных комонад и прочего, да, в алгебраический сеттинг. И есть еще так называемые кристаллические схемы и так далее. Что же очень интересно. То есть было бы интересно строить физику там над полем конечным, например. Или конечным типа, да. Что-то такое.
Мне то же самое интересно непосредственно в сеттинге гладкой геометрии. То есть Мне кажется, что вот классические точки зрения на это очень много упускают. То есть, мне кажется, если думать об этом, вот как мы сейчас мыслим там в производных инфинити-стаках, то там вот те же самые понятия, если они, в общем, много глубже будут раскрываться, как-то вот весь, ну, в общем, то есть, ну, те же объекты, да.
Да. Но вот самое главное, что все-таки дух курса, он такой достаточно технический. То есть мы ставим четкую задачу найти расширение, значит, теории гравитации так, чтобы вот она хорошо формулировалась топологически. Вот. И, собственно, это решение, как и любое решение о глобализации, ну, как и любое решение задачи о глобализации чего-либо, она решается в контексте дифференциальных когомологий. Вот. То есть мы заменяем формы на связности, грубо говоря. И здесь происходит что-то подобное. Вот. И мы видим, что тогда простой логикой, простыми рассуждениями мы видим, что вообще гравитация это должна быть очень странной теорией поля. Вот, по сути, вот тем, что мы назвали параметризованной теорией поля. Вот. И математика как бы усложняется. Ну вот. То есть
А можешь сказать, вот ты писал кратко в чате, но, может быть, повторишь, может, более подробно, какие реквизиты, кроме вот там, видимо, инф-категорий, ну, про топы ты собираешься рассказывать, инфлопсы, кажется, ты говорил, что, если я правильно сегодня разобрал, что ты будешь рассказывать сегодня, в смысле, в дальнейшем.
Нет, ну, конечно, как это сказать?
Ну, типа, вот реквизит по инф-категориям я уже предложил.
У меня план такой. То есть будут, естественно, определения. То есть такие основные. Но, например, доказывать кучу лем о свойствах топусов я не буду. Но я буду во время вот каких-то доказательств теорем, которые используют какие-то свойства. Там, да, например, что, не знаю, эффективный эпиморфизм это то же самое, что один эпиморфизм. Да? То есть вот все. И если я буду этот факт использовать, я говорю, вот это вот есть, и это можно доказать в топусах. Вот, то есть планируется примерно делать так. Пререквизиты, ну, в принципе, ну вот, не знаю, я их пересмотрю, может, но, наверное, они остаются такими, что все-таки какое-то знакомство иметь с тем, что такое топусы, что такое бесконечность категории, нужно. Вот. Ну, а физика, да физика, ну, просто слышать. То есть знаешь, что такое Лагранжан, и все. Как бы.
Ну, вот, дифференциальные когомологии, ты будешь рассказывать с нуля, как-то в том виде, как будешь...
Дифференциальные когомологии, в принципе, там рассказывать я буду, так там и немного рассказывать. То есть, по сути, про дифференциальные когомологии можно поступить с ними так. То есть у нас есть Браун представимость для обычных когомологий, например, в топусе. Вот, и мы определяем дифференциальные когомологии в стиле, как это делали еще там Салливан и другие, через пулбеки всякие. Вот, и дальше мы следуем Бюнке и другим товарищам и доказываем представимость Брауна для дифференциальных когомологий. То есть мы говорим, что вот у нас есть когезивный топус, у него есть такие-то модальности, и как бы эти модальности для каждого стабильного гомотопического типа, они строят гексагон. То есть такую диаграмму, которая характеризует дифференциальные когомологии. То есть там, в принципе, действий немного. По сути, просто обсудить модальности и построить гексагон. Вот.
Но это уже вот как бы уже как бы после переосмысления этой темы Урса, а вот есть еще как бы какое-то классическое видение, ну то есть там
есть.
которое
Но
может...
мы его, да, то есть вот люди начинали с с У1 когомологии, вот. То есть там появились когмологии Делиня. Вот. Это как раз-таки первые из примеров дифференциальных когмологий. Вот. Ну да, классические примеры есть, конечно, но мы будем работать в духе Урса. То есть мы берем модальности и с помощью модальностей на гезивных топосах сразу строим диаграмму для дифференциальных когмологий. Вот.
Понятно. Ну ладно, интересно будет все это
Ну, вот
посмотреть.
примерно так.
А мы всегда онлайн будем или мы очно будем?
Очно, возможно, что-то будет, если придется много писать. Вот. Но ну, как бы в основном я бы хотел, наверное, в рамках презентаций, потому что, насколько я знаю, все-таки зрителям удобнее презентации. И ходить они не любят куда-то. Вот. Поэтому, конечно, как что-то проведем, наверное. Особенно летом мы будем там развлекаться. Я думаю, в летней школе тоже что-нибудь сделаем. Вот. Но в основном, конечно, презентации.
А ты думаешь, какое-то продолжение делать этого курса на лектории или что?
Ну, просто на лектории, может быть, не знаю, либо в форме докладов что-то сделать. То есть будет ли какой-нибудь гомотопический семинар. Вот. И на докладе можно будет...
Это ты про не лектория, это ты про конференцию доцентов уже?
Нет. Ну, именно в рамках лектория. То есть меня, например, Вася как тоже звал, когда он теорию когмологии читал. То есть я доклад сделал по этим факториальным языкам. Вот.
Да.
И как бы в такой форме, может быть, я тоже что-нибудь подготовлю. Ну или курс, если буду свободен. Вот. Но и если что, что-то непонятно, вы пишите в форуме. То есть, вот, то есть... проблемы, то пишите, я каждому отвечу. Ну вот. Так. Ну, в общем, если нет вопросов, то на форуме я вот сегодня прикрепил курс лекций по стандартной модели. Вот, его читал недавно ушедший значит, из жизни Александр Андреевич. Вот. И, ну, мне разрешили использовать, поделиться презентацией. Они очень полезные. Вот. И в целом, то есть вот, если там все прочесть, то станет картинка ясной, вот, о том, вот как устроены три взаимодействия в природе. Сильная, слабая и электродинамика. Так, шаг пропал.
Я не пропал, я просто выключил звук.
Все в порядке. Ну, все тогда, я не знаю, что еще обсудить. Ну вот,
Да, если нет вопросов, надо расходиться.
да, хорошо.
Спасибо, до свидания.
Угу, до свидания.
Всем до свидания, пока.